This graph displays the frequency of the United Kingdom's national grid. By design, the entire alternating current network must remain perfectly balanced at exactly 50 Hz. To maintain this line, electricity supply and demand have to match millisecond to millisecond. If a major baseload plant fails, or millions of appliances draw power simultaneously, demand instantly outstrips supply. When that happens, the grid frequency drops. To recover the frequency, the grid needs a massive injection of power. But a traditional thermal plant takes hours to reach operating temperature, and a nuclear reactor can take days to ramp up. Arresting a frequency collapse before the network cascades into a blackout requires a kinetic battery. It demands a facility engineered to react faster than a grid can fail. Built deep inside the Illiterate Fowl Mountain in Snowdonia, Wales, Dinorwig Power Station operates largely out of sight within the boundaries of a national park. Beneath the surface, civil engineers excavated 12 million tons of rock to create a subterranean machine hall 180 meters long. From this cavern, Dinorwig can inject 1,320 megawatts of electricity directly into the national grid in exactly 12 seconds. The facility operates as a highly optimized electromechanical conversion system. To isolate exactly how it achieves this response time, we have to freeze the operation and break down the specific electrical and mechanical sequence occurring within that 12-second window. This diagram shows a stationary Francis turbine and its attached generator rotor. At a complete standstill, initiating the rotation of a 450-ton steel mass takes 90 seconds just to overcome physical inertia. Dinorwig bypasses this delay by holding the machines in a standby state known as spinning in air. The generator remains synchronized to the grid, drawing roughly 4 megawatts of power to keep the rotor spinning at a synchronous speed of 500 revolutions per minute. To accomplish this without damaging the equipment, high-pressure compressed air is continuously injected directly into the turbine casing, keeping it entirely clear of water. Removing the water eliminates hydraulic drag. The massive steel rotor spins freely, maintaining its synchronous speed without pulling an excessive load from the wider grid. By preloading the kinetic energy into the system and maintaining synchronization, Dinorwig circumvents the mechanical startup penalty. This makes a 12-second response physically possible. At the 5-second mark, the station receives an emergency load pickup command. The compressed air vents, and a 160-ton Android spherical valve rotates open. This component executes the release while holding back water at 80 bar of design pressure. This cross-section illustrates the primary energy transfer. Water from the upper reservoir drops 546.7 meters down a vertical shaft, striking the Francis turbine runner with extreme hydraulic force. To prevent the resulting pressure fluctuations from causing destructive cavitation on the metal blades, civil engineers positioned the turbine floor exactly 71 meters below the surface level of the lower reservoir. This guarantees the necessary net positive suction head. Managing this highly pressurized hydraulic impact without destroying the cavern's machinery is the strict physical requirement for generating massive electrical output. This wireframe tracks the mechanical rotation as it travels up the vertical shaft into the salient pole air-cooled generator motor, where 12 electromagnetic poles convert the physical motion into an alternating electrical current. The 6 generator motors operate simultaneously, outputting 18 kilovolts of raw electrical power into the facility's busbar galleries. Before this power can leave the machine hall, it passes through generator circuit breakers. These protect the highly sensitive 340 megavolt ampere power transformers by clearing potential short-circuit faults. First Hydro is currently modernizing this layer of protection, replacing the facility's 1970s-era air blast circuit breakers with state-of-the-art ABB HEC 130 SF6 gas-insulated switchgear. The original air blast technology required a complete mechanical overhaul every 3,000 operations. The new SF6 units are rated for 20,000 operations, extending the maintenance interval to 20 years. Lengthening the life cycle of the switchgear directly minimizes plant downtime. It ensures the station remains fully operational and prepared for the next rapid response grid event. At exactly 12 seconds, the transformers step up the generation voltage from 18 kilovolts to the 400 kilovolts required for transmission on the national supergrid. Because the station sits within a protected national park, Moving this power requires a 12-kilometer underground cable route connecting the mountain to the Pentir substation. This diagram compares the internal layers of the site's original 1970s oil-filled cables against their modern equivalent. The National Grid is executing a £1 billion replanting project to lay 1,500 tons of solid-state, cross-linked polyethylene cables along the route. Achieving 1,320 megawatts of generation deep underground serves no purpose if local transmission infrastructure cannot safely deliver that capacity to the rest of the country. In 1984, Dinorwig primarily operated to absorb excess baseload capacity at night and cover sudden demand spikes, like the surge of electric kettles after a television broadcast. This comparative chart shows a structural vulnerability in the modern grid. Heavy spinning thermal plants are retiring, replaced by solar arrays and wind turbines that connect via solid-state inverters. These renewable sources provide zero physical inertia. When grid supply and demand diverge, the rate of change of frequency accelerates. Dinorwig counters this through synchronous inertia. Its 6 synchronized 450-ton steel rotors provide a massive physical shock absorber against sudden frequency deviations. To protect these spinning assets, operators have integrated SCADA systems with the Andritz-Metris platform, utilizing real-time sensor data across the hydraulic and electrical systems to execute predictive maintenance before mechanical failures occur. As the power network transitions towards net zero using digital and intermittent resources, its ultimate stability relies on the unbreakable physics of high-mass spinning steel.